Good evening, ladies and gentlemen, and welcome to the Geological Society of London, and to this, the 7th 2016 Society London Lecture, entitled A Little Goes a Long Way, Researching Ash Clouds and Abrupt Climate Change. My name is Nick Billam. I'm Director of Policy and Communications here at the Geological Society, and it's my great pleasure this evening to welcome our speaker, Professor Siobhan Davies of Swansea University. Now, from the Greenland ice sheet to the depths of the North Atlantic, microscopic ash particles can help identify the drivers of rapid climate changes during the last glacial period. Instantaneously deposited over vast areas, this geochemically distinctive volcanic material gives us a powerful dating and correlation tool called Tephra Chronology. Just a few tiny particles have the potential to correlate paleoclimate records precisely from the ice and sedimentary realms, and to help us address why the world's climate occasionally changes so abruptly. Here to tell us about this subject this evening, we welcome Professor Siobhan Davies of the University of Swansea, where she is Professor in Physical Geography. Siobhan was awarded the Philip Leverhulme Prize in Geography in 2011, the Lyell Fund of this Society in 2013, and was elected a Fellow of the Learned Society of Wales in 2015. She frequently contributes to public engagement activities in Welsh and in English, and is currently presenting a 5-part documentary series on climate change for Channel 4 Wales, S4C. Ladies and gentlemen, please welcome Professor Siobhan Davies.
Thank you very much. It's a great pleasure to be here, and I'd like to thank the Geological Society for the invitation to come here and share my research work with you. So today's talk will be all about volcanic ash and how we can use volcanic ash as a way to improve our understanding of how climate has changed in the past. Now, what I want to share with you is how a little bit of ash can certainly go a long way, both in terms of how it's spread over geographical areas, but also in terms of the scope of this technique and how we can use it to address some big scientific questions. So I exploit past ash clouds and try and piece together these ash clouds that have dispersed ash over wide geographical areas and use them to try and address why climate has changed abruptly. Now, today's lecture will be in 2 parts. In the first part, I want to look at why volcanic ash is so valuable. Now, some of you will be familiar with the technique of Tephra Chronology, and I want to share with you the basic principles of that technique, how it works, and why is it so powerful. The technique itself has undergone a bit of a step change, a bit of revolution in how we actually apply the technique, and I want to just explain and elaborate on that in the first part. And then in the second part, I want to delve into how I'm using the technique in order to try and address abrupt climate change. So many of you, most of you will know that when a volcano erupts, it'll produce tephra. And tephra is the term that encompasses all the pyroclastic material, all the airborne material produced during a volcanic eruption. Now that will include the large fragments, the bombs that are deposited very close to the volcanic centre, the lapillae that are transported a little bit further, and then you've got the ash, the finest grain component, and it's that ash that undergoes widespread dispersal. And it's that ash component that I'm most concerned with. Now, you'll hear me today talking about tephra and hear me talking about ash. Now, strictly speaking, the tephra includes all of the airborne pyroclastic material from the bombs, lapillae, and the ash, but it's become synonymous with ash. Tephra and ash are often used interchangeably. And so when you hear me talking about tephra, I'm actually talking about the finest grain size component, the ash component, which includes the tiny glass particles that are produced from the fragmentation of the magma during the volcanic eruption. So it's the ash that undergoes the widespread dispersal. And I'm sure you'll all be familiar and remember the 2010 Eyjafjallajökull ash cloud that led to chaos in Europe, disrupting flights. And this is a prime example of a modern day eruption. Wasn't particularly a big eruption, but it led to widespread ash dispersal over large geographical areas. So I work on ash clouds like this particular eruption, but I look at ones that have occurred in the past, piecing together the widespread dispersal based on the preservation of ash within different records. So when a volcano erupts, we have this widespread dispersal of ash over a large geographical area, and we have instantaneous deposition. Deposition of ash, blanketing a land surface, blanketing, falling on ice, falling on the oceans, falling on lakes, falling on peat bogs, blanketing a land surface, and that deposition occurs within a few days or within a few weeks. And in geological terms, that is instantaneous. That represents a very short-lived event. And what happens then is that ash becomes incorporated within our geological sequences, providing us with a marker horizon or an isochron, a deposit of equal age that we can find in different areas. And so what that means is that we have a catalogue of volcanic ash events preserved in different records. And this image that you see here is a soil sequence near the Hekla volcano in Iceland, where there are some beautifully preserved ash deposits. There's one here at the bottom, one here in black, and then there's a white deposit here, and then there's another one at the top. And notice just the sharp contact here, the really sharp lower contact that marks this short-lived instantaneous deposition of ash. So it marks this fixed point in time, instantaneous deposition. And that's what makes it so powerful, because it leaves these marker horizons within our geological sequences. So near the volcanoes, the deposits are really thick, and as we go further away from the volcanoes, the deposits become thinner. But we can still see them. This black band here, around 2 centimetres thick, is incorporated within a lake sediment sequence from the Faroe Islands. And then we've got another lake sequence here from France that contains a volcanic ash. And again, some ash deposits that are around 1 centimetre thick, a few millimetres here, and a few centimetres here preserved within ice cores. So the deposits get thinner as distance increases. How do we know which volcano has generated this ash? Well, the clever thing about this technique is that each tephra or ash deposit has a distinct geochemical fingerprint, a geochemical fingerprint that can be traced back and reflect the source of the volcano, the source volcano, but also provides us with an identity tag. So the tephra produced from an individual volcanic eruption has a tag which we can then match together the different ash deposits in different areas. So normally we look at major elements. So we've got silica here in a plot, a biplot of silica. This is potassium. And there are distinct compositional envelopes. A distinct Icelandic envelope, a Mediterranean Campanian field, and an Eiffel field, and also the Massif Central. So we can pull these apart depending on the origin of the tephras. And in Iceland, then, we've got distinct signatures reflecting the different volcanic centres within Iceland. So the basic principles, then, the widespread dispersal of ash, the instantaneous deposition, preservation and burial within our geological records and with a distinct geochemical fingerprint, these basic principles means that we have a timekeeper or an isochron that marks a fixed point in time, and this is the technique of Tephra Chronology. Now, if you're familiar with the technique, you'll know that this isn't a new technique. This was a technique, the founder of the technique and the person who coined the term Tephra Chronology actually worked in Iceland back in the 1940s, and he coined the term in 1944 during his PhD studies. He was a student at Stockholm University and a bit of a polymath. He worked on glaciological issues, he worked on archaeological sites, as well as volcanological sites. And he was the one that recognised the potential of using volcanic ash deposits in Iceland and matching different sequences in order to provide a chronological framework for environmental history, archaeological changes in Iceland, glaciological changes, and so on. So in 1944, he coined the term Tephra Chronology. And if you've been to Iceland, hopefully you will have seen distinct soil sequences that are stripy. There are distinct barcodes within the soil sequences, and these volcanic ash deposits, these stripes or this barcode can be traced over different sequences and used to match the different tephras, giving us our age framework. So Tephra Chronology, not a new technique. So where does my work fit in? Well, when friends and family ask me what I do, and I tell them I work on volcanoes and volcanic ash, I get two different responses. One, the look of sheer horror, and I can see them imagining me working on the flanks of a volcano with a bucket in hand, ready for the eruption to happen, ready to collect my samples. Some just look at me with just utmost respect and admiration and just, I think, see me as some sort of hardcore geologist working in a very extreme environment, a risky environment. But I really hate to disappoint you because I don't actually go anywhere near a volcano. I actually work hundreds, if not thousands of miles from volcanoes. And I don't have a bucket, I don't have a spade. All I need is a microscope, because my work goes beyond where we can actually visibly see these ash deposits and actually to areas where it's not traditionally associated with tephra research. So to areas where it's quite unusual to find some of these to find some of these ash deposits. So I work in the microscopic realm. And I work in icy environments, I work in muddy environments, but always a long way from the volcanoes themselves. And I would work on cores, sediment cores like these ones here. And when I examine the cores, there's no indication within the cores themselves that there's any ash deposit present. There's nothing visible when I look at them with the naked eye. But by looking at these cores, centimetre by centimetre, processing the sediment, removing most of the host material and looking for tiny glass particles or ash particles, I can actually find them by using microscopy techniques. So we're going beyond the visible realms to the microscopic realm. Sometimes I find 5 grains, sometimes I might find 127, sometimes I might find 200. But the common thing is that you can't see them when you're just looking, visibly examining the cores with the naked eye. So I collect glass particles. Just like these ones, they are present in very low concentrations, so they're not visible to the naked eye. And we tend to think of them as hidden layers. And the technical term for them is cryptotephra. This is the term that's been coined, cryptotephra deposit. And the crypto comes from kryptein in Greek, meaning hidden. So we look for cryptotephra deposits that contain these low concentration of ash particles. And we use a whole host of different techniques, different extraction techniques that will vary according to the sediment that we're looking at. So for peat, for example, which is mostly organic material, we would just burn it in a furnace, remove all the organic material and look to see what is left. And the ash will not be burned at the temperatures that we're looking at. So the ash particles should still remain. If we're looking at very mineral-rich deposits like lake sediments or marine deposits, we would use a density separation. We can float off the ash particles, float them from the mineral-rich materials, and then concentrate them and look under a microscope to see if we can find any of these glass particles. Or if we're looking at ice, we just melt the ice, centrifuge the water, remove the water, and see what's left. And so you get the picture. We basically remove everything and see what is left in terms of the microscopic ash particles. So I collect glass particles, and you can think of me really as looking for needles in haystacks. I look in various haystacks, from peat, from ice to marine deposits, and the common theme is looking for these needles, using the microscopic techniques in order to find these ash deposits. And if we can find them, they still represent the isochrons. We just can't see them when we're looking with the naked eye. So we're dealing with just a few grains, a few particles, and so we have to be very careful. We have to analyse grain by grain and analysing their geochemical composition. Each grain will give us a fingerprint and a geochemical signature, and we use single grain major element analysis where we have to be very careful in terms of micro-manipulating the deposits. So it's painstaking, meticulous work that requires a lot of patience in terms of preparing individual grains. So we go from the picking individual grains and isolating them with our extraction techniques to the use of electron microprobe analysis, which gives us around 10 major elements, and that's what gives us our compositions. So the technique has really changed from the macro scale to the micro scale. And this has really undergone a step change, which now means we can move and search for these volcanic ash deposits in areas where it's quite unusual or has been quite unusual to find ash deposits. And to demonstrate this, I want to show you the distribution of an ash deposit from the Katla volcano 12,000 years ago. Now, this is a tephra deposit known as the Vedi ash. So it erupted from Katla around 12,000 years ago. And each black dot here represents a core where a visible record has been found. So until we started dabbling in the microscopic realm, the distribution of this particular tephra was constrained to the North Atlantic region and also to Western Russia. Ignore this hatched area, they are thought to be ice rafted, but the atmospheric dispersal was limited to the North Atlantic and Western Norway region. But by looking in the microscopic, for the microscopic or these cryptotephra deposits, the ash limit and the geographical limits of the ash cloud from Katla has been extended to Scotland, to Sweden, to Western Russia, the Netherlands, the Alps, and even as far south as Slovenia. So initially we thought the ash cloud was limited to this very constrained area of the North Atlantic, an area areas very close to Iceland. But in actual fact now, the geographical dispersal has been extended quite considerably. And so this really has led to a change in application and how we are actually applying this technique. Rather than just concentrating in areas very close to Iceland, we can now suddenly start looking at and linking together different geological records that contain the same volcanic ash deposits all the way from Slovenia all the way to Greenland, based on the position of these ash deposits. So the technique has undergone a bit of a revolution, a step change, where it's really progressed into new areas, which means we can now address some big questions. So this then brings me on to my own work, and we're going to go on a journey. We're going to start by going to the Greenland ice sheet. And in the Greenland ice sheet, cores have been taken from the surface all the way down to bedrock. And those cores can be thought of as time machines that contain clues about how the climate has changed in the past. And then from the heights of the Greenland ice sheet, we'll delve into the depths of the ocean, to the sediment that's accumulated on the seabed and the seafloor, that also contains information about how the ocean has responded in the past. So we've got two climate repositories here, the Greenland ice core and the North Atlantic marine cores. So the big question, the overarching question that's been my focus for the last few years is, why does climate change abruptly? Now, during the last glacial period, between around 110,000 to around 11,000 years ago, we know, based on evidence from the Greenland ice cores, that the climate during the last glacial period changed very, very abruptly. And there were several abrupt events that characterized this period. So the evidence initially came from the Greenland ice cores, and here's just a tiny section of a 3,000 metre long ice core. This is just 3 metres, but the ice cores themselves are actually 3,000 metres in length. And so from the ice cores, there's a record of oxygen isotopes, and the oxygen isotopes gives a direct record of changes in air temperature. So the red wiggles you're seeing here can be thought of as changes in air temperature. So at the top of the graph, the changes, it's warm temperature, at the bottom, it's cold. So during this is time along the bottom here, and during the last glacial period then, we have distinct abrupt events where we see abrupt warmings of about 8 to 16 degrees C changes in air temperature, 8 to 16 degrees C temperature jumps occurring within decades, gradual cooling and more rapid cooling. And we see several of these events, around 25 of these events characterised the last glacial period. They were first of all recognised in Greenland. Since they were found in Greenland, a number of different scientists then started looking at different repositories, climate repositories, to see if indeed these changes could be found. Because finding these abrupt events really revolutionised our understanding of how climate has changed in the past. They really didn't follow the pattern that we expected to find. So these abrupt climate changes can be thought of as a real baffling thing for climate scientists. So people started looking in other repositories, and they found them in a number of different records, from lake sediments, from speleothems and cave deposits, and also the North Atlantic marine region. There's evidence also of these events occurring in Antarctica, but they take a slightly different form. So they're also found in the marine environment, and in the marine environment, by looking at the polar foraminifera species. Foraminifera species are very sensitive to changes in sea surface temperatures, and by looking at changes in the abundance of the foraminifera species preserved in our marine cores, we can piece together and reconstruct changes in sea surface temperature. So the blue here represents sea surface temperature changes. And we can see, hopefully you can see, very similar patterns recorded in the oceans. We see very rapid changes in sea surface temperatures, gradual cooling, and more rapid cooling in the sea surface temperatures. So the similar patterns also seen in the ocean environment. Now, when this became apparent, what people then started doing was aligning them. They started matching these records based on these rapid transitions. These dotted lines represent where they've aligned their records, assuming that these rapid abrupt events have occurred at the same time across a geographical area. And that can lead to a bit of a problem. So if we look at one of these particular events, now this is just a schematic of one of these events. We've got red is air temperature from Greenland, blue is sea surface temperature from the ocean. So 8 to 16 degrees sea warming, massive temperature jumps occurring within a human lifetime. Key question then, what is driving these abrupt events? That is what we really need to understand. What is the driver that is making the climate jump in such a way during the last glacial period? Now, very simply, we can think of two different hypotheses have been put forward. Some believe that these changes and the driver for these changes reside in the ocean, and that disruption to the oceanic circulation has led to the occurrence of these rapid and abrupt events. Whereas others think that the trigger for these events resides in the atmosphere, and that massive reorganization in atmospheric dynamics is the trigger for these events. So we've got two competing hypotheses, ocean versus atmosphere. So in order to try and test these different hypotheses, we need to try and understand, if we want to know whether the ocean is the trigger or whether the atmosphere is the trigger, we need to really understand how they're responding to one another. We want to see if the ocean is responding first or whether the atmosphere is responding first. So we need to look at the response, the relative response, so the phase relationships between the ocean and the atmosphere. But we've got a huge problem. And that is because of the dating uncertainties. Now, I told you that people are just aligning them based on the rapid transitions. By aligning them, we're assuming that they're happening at the same time, and we can't then test whether the ocean is leading the atmosphere and vice versa. So we've got a problem with our dating uncertainties. Now, in the ocean environment, radiocarbon technique, the radiocarbon dating technique is the commonly applied technique. But it doesn't give us an exact age. It doesn't always give us an exact age, and it's often associated with an error. So in the marine environment, we might have a radiocarbon age that has an error of plus or minus 300 years, or even in some instances, 700 years. So these errors actually are larger than the duration of the event. So we've got errors in the ocean records of up to 700 years, plus or minus 700 years, whereas these events are really short-lived and happening within decades. So our dating uncertainties are just not good enough for us to be able to align and compare the responses between the ocean and the atmosphere. So hopefully by now you'll know what the solution is, or what I'm trying to do and what my solution is, and that is to use the microscopic ash layers. Use these common tephra deposits that hopefully we can find between the atmosphere, within our ice cores, and within the ocean in order to provide us with a fixed point in time, our isochrons that allow us to then match these records based on the position of the ash and then compare the response. Now, just to stress, the volcanic eruptions themselves don't have anything to do with the climate signals. They just provide us with constraints, fixed points in time to constrain our ice core records to our marine records in order to allow us to look at the relative response, to look at how the ocean is responding versus the atmosphere. That is my big goal. Now, what I want to share with you is some of the trials and tribulations that we've gone through in trying to get to this. But this is my solution, my proposed solution to try and address this big question of what is driving these rapid events. So we're trying to assess the leads and lags, trying to assess the differential response between the ocean and the atmosphere in order to test these competing hypotheses. And only then can we really understand why the climate is changing abruptly. Now, I hate to disappoint you, but I can't really give you this answer now, but it just gives you a framework, because we're still perfecting this, still refining the work. But I want to show you the work and where we're at the moment in terms of trying to answer this big question. This big question provides the overarching framework for the work that we do. So over the last few years, I've been working on a project along with research team members working on bringing together the ice and the marine cores. So we've got a range of ice cores that we've looked at from Greenland, working in collaboration with the Ice and Climate Group from the University of Copenhagen. And then the red dots here are cores that have been drilled from specialist ocean drilling vessels that have cored into the ocean sediments. We've mostly been working on archived cores that have been worked on by a number of different teams from Europe and the US, and they've kindly provided us with samples from these different cores. So we've got the ice and we've got the marine network. If we first of all turn to the ice cores, now the ice cores, I've told you, are very, very special. It provides us with a very long record, 3,000 metres at its longest. This is the 3,000 metres, the longest ice core that's been drilled from Greenland, giving us a very detailed record of how climate has changed in the past. Now here we've got a cross-section of an ice sheet. The ice cores are taken from the highest point from the ice divide, so that they're not affected by any ice flows, any effects of the ice flow. The ice sheets themselves accumulate annually. During the winter, there's a bright layer that represents winter snowfall. And then in the summer, because there's more melt, the layer left is slightly darker because the impurities are concentrated. So we've got a white winter layer and we've got a dark summer layer. And together, they can be thought of as tree rings. These provide us with our banding and our annual layer accumulation within our ice cores. And so what we find are distinct bands like these that can be identified and represent year-by-year changes in the atmosphere. We've got a phenomenal detailed record from the ice cores. And so we can count from the top, and we've got a very detailed record going in Greenland, going from the present day all the way back to the last interglacial around 120,000 years ago. So a very detailed record from Greenland. Some pictures with you of the Greenland ice core work that I've been involved with. These are pictures from a drilling campaign in northeast Greenland that I was involved with a couple of years ago. A 3-metre section that's just been drilled and brought to the surface. And here you can see the work in the processing trench, where they are cutting, and every different group that's applying different techniques on the ice would get their different portion. The ice core work is a huge logistical operation involving a number of different scientific groups, and everyone wanting their different portion of ice core in order to perform the different techniques. So they would look at isotopes to reconstruct temperature. They might look at the air bubbles preserved within the ice in order to reconstruct changes in CO2 and methane in the past. And my particular work is to look at the tephra component. So looking for tephras within these ice core records isn't actually new. And back in the 1990s, there were attempts to look at the tephra work and the tephra horizons preserved within the ice, but they always focused on those visible layers. Visible layers that we can see, like these ones, or they focused on where there were chemical signals in the ice that suggested that a tephra might be present. So they were looking at sulfate and acidity layers preserved within the ice. But the work was really targeted targeted on these visible layers or well-known eruptions, particularly within the historical period, when they knew big volcanic eruptions had occurred. And so they only look at a few portions of the ice core sequences. What did they find? Well, this is what they found. The grey record here is the temperature changes over time recorded in the ice cores. So this is the present day, and this goes back to around 123,000 years ago. So the grey represents the surface temperature, the air temperature changes as recorded in Greenland, and then the red represents the ash deposits that they found during the 1990s. And you can see some found in the historical layer at the historical period, some of them during the last 1,000 years, some of the well-known eruptions in Iceland. There's a couple of visible layers found around 10,000 years ago and 12,000 years ago, and then the big Ashton 2 eruption around 55,000 years ago. That is what they found based on the work in the 1990s. Because of the work in the microscopic realm had advanced and progressed, and the success of finding microscopic ash deposits, during my PhD, I started working on these microscopic deposits within the ice itself. And that has resulted in intensively sampling the ice cores, sampling meters, thousands of meters of ice that's stored within the archives in Copenhagen. These are videos of the huge freezers that they've got there that are floor-to-ceiling full of ice core samples. And so we spend sampling campaigns in the freezers, weeks on end, sampling tiny portions of ice. You can see it. We take a tiny sliver from the edge of the archived ice cores. We take the portion that nobody else wants. But nonetheless, we get our portion. It's a tiny part, but we do get a part of the ice core sequences. So the ice itself then, we work very hard in Swansea. With the ice itself, it's put into sampling bottles, and all those bottles then are shipped back to Swansea. The ice is melted, we remove the water by centrifugation, and then we actually look to see what's left. And so we've got thousands of slides like this. Each and every slide contains an individual sample, and we've got boxes just like this one full of slides representing the thousands of meters of ice that we've sampled. And just to give you a flavour of what my PhD and postdocs are working on, these are the fields of view that they're searching through. These are typically what they're seeing down a microscope. Sometimes they'll find lots of dust, sometimes they'll find a few mineral grains, and it's within these fields of views that they're looking for these microscopic ash particles. And this has worked really, really well. Now, you'll remember this is what they found in the 90s based on really targeted searching and targeted sampling. Remember, each red line represents a volcanic deposit. Over the last few years, we've sampled a huge thousands of meters, represented by the green shading in this particular figure. And as a result, the volcanic history and the volcanic record from Greenland now looks like this. So we found a huge number of microscopic ash deposits, over 200 individual ash deposits. And this really can be thought of as our catalogue of volcanic events. It's probably, if I can say so, it's probably one of the best catalogues of volcanic events that extends back to the last interglacial. It's very detailed. Remember, in Iceland, beyond 10,000 years ago, there's very little evidence that's remaining that records volcanic history. A lot of the evidence in Iceland itself of previous volcanic eruptions before 10,000 years ago has been removed by glaciation, but they're preserved. Some of these eruptions are preserved within this record in Greenland. And because we can count the annual layers within our ice core, then we can provide age estimates. We know exactly when these eruptions have also taken place. So we can provide age estimates on every one of these different volcanic eruptions that we found. Most of them, unsurprisingly, are previously unknown volcanic events, based on what we know and what's been published in the literature. So it's giving us a really new insight into the volcanic frequency, of areas such as Iceland. And the records then, this particular record is dominated by Icelandic products, dominated in particular by basaltic products from Katla, from Grímsvötn, and from Kverkivol. Now, I was really hoping that we could find some of the big tropical eruptions. You may have heard of Toba, a big eruption 70,000 years ago. I was really hoping we could find some of these big eruptions from the tropics, but unfortunately, they remain elusive. We haven't been able to find them. Now, that's not to say they're not there. We just haven't been able to find them yet. But we have sampled quite extensively. Maybe in the future, when there are more ice cores drilled, they may actually be found. So we've got this record, a very detailed record of volcanic history, dominated by Icelandic product, particularly basaltic products. Now, one of the challenges and one of the problems, although I'm very pleased with the record we've got, what we are finding, this dominance of basaltic products can be a little bit of a problem for us. And what this means is that we've got, rather than having distinct geochemical fingerprints for our volcanic ash deposits, we have, in some instances, quite an overlap in our different tephra deposits. The different colours here represent the different deposits, and often you'll see they are overlapping. So sometimes we don't have a distinct geochemical fingerprint because of the dominance of the basaltic eruptions. The basaltic eruptions tend to generate and tend to reflect similar. Different volcanic eruptions from the same source tend to produce similar and indistinct geochemical fingerprints. And that can cause us an issue when we're trying to use them as our identity tags to trace the same eruptions within the marine environment. So can we find ash deposits in the marine environment? The answer is yes, we can, but it is a challenging environment to work with. This is a really challenging haystack. Now, in the ice, we were just melting the ice, seeing what was left. In the marine deposits, in the marine environment, we've got a lot of mineral material that we have to try and remove and sift through to actually find our microscopic ash particles. Now, in this slide, this is just a summary of what we found in the marine environment, and each cylinder here represents different cores, different records from the North Atlantic region. We've got the ice and the temperature record in blue here, and the colourful layers here, colourful lines represent the different tephra deposits. And you should see immediately that we are actually finding far fewer tephras in the marine environment compared to the ice core tephras. We're not seeing as many tephras at all within the marine environment. And what we're also finding is that the ash deposits are of quite limited distribution in the marine environment. We're not finding, apart from a few exceptions, we're not finding the same tephras in all cores. Sometimes we're finding them just in one core, sometimes in two, but often they can't be thought of as ubiquitous or found in all our different cores. So you can see here with ferromarine ash, this particular eruption here found in this core and this core, but not in the other cores that we've looked at. There's one exception, this one, which is found in all cores around 55,000 years ago. So limited distribution, which is a little bit disappointing, and some are exclusive to the marine environment. And that just demonstrates different transport pathways. We've got some eruptions taking ash to Greenland, and then other eruptions that have only taken the ash to the North Atlantic region. But we have some that are depositing ash in both directions and in both archives. So we are finding some, but not as many as we initially hoped. And because of the issue with finding so many basaltic eruptions with similar fingerprints, we've had to resort to an added level of fingerprinting. And that's to do with using trace elements. As well as looking at major elements, we also have to look at trace elements, and we're working with a colleague at Aberystwyth University, Nick Pierce, who's in these images here, and he's using and helping us use laser ablation ICPMS, which is a technique that allows us to analyse elements that are present in very low concentrations within our individual particles. It's quite a challenging technique, but it is working and we are using it, and it's become crucial for our work. And in order to demonstrate how important it is, I want to share with you an example of one particular tephra that we found. We found this here is, these different wiggles here represent different climate records from one marine core in the North Atlantic. So we've got a record of sea surface temperature here, we've got calcium changes, and then we've got a record of ice rafted changes, all from the same core. And then we've got the temperature changes in Greenland from the ice, and the red bars here represent all the tephras we found. And my postdoc, Peter Abbott, was working on this core, and he found one distinct layer within this marine core, shown in red here, and he thought that it actually matched one of these tephras preserved in the ice core, just shown there in the green bar. Major elements show a really good match. There's an overlap between the compositional signature from the marine deposit and the ice core deposit. And I got really excited with this particular example because this particular ash deposit was constraining a rapid warming, and it also suggested that the ocean was actually responding before the atmosphere. So I thought we had our answer, that the ocean was changing before the atmosphere. So I thought we could actually answer this key question. We tested with trace elements, And unfortunately, although we've got the overlap in the major elements, the trace elements actually showed that they were from two different eruptions. So even though they were similar in major elements, the trace elements suggested that it was a different eruption, probably from the same source, but with a very different trace element signature. And I think this observation was really disappointing, but also very, very important for us to realise that we couldn't just rely on major elements, particularly for the basaltic eruptions, and that we also had to delve into the trace element word. And I think this is going to lead to a new field. We've got a lot of work to do on understanding how trace elements vary between different volcanic eruptions and also within a volcanic eruption as well, because there are potentially phase relationships, phase changes that could happen within a particular volcanic eruption as well. So this is a big cautionary tale that we couldn't just rely on the major elements, but we are finding common tephra deposits and the trace elements do match. So we are able to do this. It does work, but there are some instances where the trace elements actually show we've got different tephras. So to go back to this then, we are finding common tephra deposits that allow us to link our ice core to our marine deposits. Now, the trace elements and the fingerprinting added a new level of complexity to our work. Now, if there are any sedimentologists in the room, I'm sure you're already thinking that there's another level of complexity within the ocean environment. And that is, how did the tephra actually get to the seabed in the first instance? Now, it's very simple. If you think about it, it's very simple with the ice core environment. We've got our eruption, the ash goes into the atmosphere, and it's deposited through the atmosphere instantaneously. That's the only way it can go to the ice sheet and be preserved within there. Within the ocean, this particular flow chart shows you the different pathways where our tephras can actually go from the atmosphere all the way to the seabed. Now, very simply, we want an eruption to happen, primary airfall, and we want it to fall to the seabed and be preserved within the geological records. But there are other complicating factors that can stop and delay this deposition. We've got iceberg calving, we've got sea ice rafting, we've got biotubation, burrowing animals, smearing the record, pushing and pulling these ash particles down within our geological record. So we've got to be really, really careful. And this is particularly enhanced when we're looking at microscopic ash deposits. Remember at the start, I showed you the sharp contact that we could see in our soil sequence in Iceland. That sharp contact we can easily see, and it marks the instantaneous deposition of ash. In the microscopic realm, we don't have any stratigraphy to go by, and what we have to look at are concentration profiles. And so we would look at concentration profiles in the marine environment, just like these ones, and we would look centimetre by centimetre down a core, recording the number of ash particles and producing shard concentration profiles, ash particle concentrations like these ones. So ideally, we want to find ones like those that really mark a distinct occurrence of a volcanic eruption and instantaneous input of ash into our marine environment. We do find some like that, but sometimes we find some where we've got a gradual increase to a peak and a gradual tail off, or we've got a very rapid input of ash here, but a very gradual tail off in the shard concentrations. Or we've got ash deposits that are very high, where we've got high concentrations of ash deposits over several centimetres, or a very low background. So the microscopic deposits in the marine environment come in all sorts of forms. We use a number of different techniques. I'm not going to go into these, but we have to assess the different microscopic ash particles and the shard concentration profiles we've got. We assess each one in turn to make sure that we are placing the position of the isochron in the right place. For example, we would usually find in this particular deposit a red bar here that represents the distinct point in time, that represent the exact time of the eruption. And we also have to assess that we are dealing with primary deposits, nothing that's secondary, transported by iceberg calving or anything like that. We want to identify primary airfall events. So there are various things that we can look at, and I can discuss these with you after this lecture. But one of the things I want to highlight, because I think this is quite cool, is using and looking at microsedimentary features. And this is something that we've been working on with engineering colleagues at Swansea, where we're delving into the 3D world and trying to visualise how a tephra is manifest and preserved within a marine core using X-ray microtomography. So think of it as a CT scanner that allows us to look inside a marine sediment record. And this is just some example of a deposit. It's actually a visible tephra deposit, this one, but we had to start experimenting with this technique in the visible realm before we can apply it to the microscopic realm. And you can see this particular deposit is really quite thick. And if you actually examine this core with a naked eye, you could see a distinct isochron. The lower boundary is really marked. But looking at it with this tomography technique, we can find that the ash particles can actually be pulled down quite a long way below this particular isochron. So think of this in terms of microscopic realm. It's even more challenging the microscopic realm because these ash particles can actually move around. So hopefully this technique will help us to address this work. And just to show you a video, what we've done, so you're essentially stripping away all the sedimentary material and just looking at the volcanic ash. This is work done by my engineering colleagues in Swansea. And one of my PhD students is taking this technique even further now, and she's experimenting with various imaging techniques and creating these wonderful, beautifully preserved 3D images of ash deposits that are preserved in different sedimentary deposits. And she is now taking this further to try and see how far we can push this technique to use it to look at the microscopic ash deposits. So let's go back to our big question. Why does climate change abruptly? And I told you I probably wasn't going to give you an answer, but just to show you where we're at with this, we've got our ice cores. We've got our tephra deposits within the ice cores, usually from Iceland. We've got our climate signals from the ice. We've got our marine cores, we've got our tephras within the marine cores, and we've also got our climate signals from the marine deposits. And so when we find the common tephra deposits, as I said, far fewer than we hoped, we are finding a few of these common tephra deposits between the ice and the marine. We can then compare the climate signals between the ice and between the marine, so giving us a record of atmosphere versus marine changes. What we are finding is that we are now beginning to look at snapshots. And I'll show you I'm going to show you a lot of wiggles, but these are climate records from different cores where we can find these different tephra deposits. So we've got a tephra deposit, the North Atlantic ash zone 2, 55,000 years ago. That's found in a number of different cores. All of the different climate curves that you can see there, all these different wiggles are from different records throughout the North Atlantic region, from the ice here to the marine environment, different cores from the marine environment. And this red layer here marks the position of our fixed point, our isochron. Now, we are still working on these particular cores, trying to improve the detail and the climatic changes that are preserved within these particular records. We need to improve the resolution of the climate records here. But just to show you how we're working and what we're working on, these are the isochrons. And dare I say it, I might be wrong, but we're still working on this. We've got this isochron marking the cooling transition at the end of what we call GI15. In this particular core, so the cooling transition has occurred at the same time as this tephra deposit has been deposited and preserved in the ice. Remember that the volcanic deposit has nothing to do with the climate signal. They're completely independent. They just provide us with a framework of looking at these things. So we've got a cooling transition. The cooling has already occurred in the atmosphere, but actually, if our placement of the isochron is correct here, and I stress if, because remember the problems relating to the marine environment, if our placement is correct in this microscopic ash deposit, then in fact the ocean is lagging behind the changes within the atmosphere. Changes in the atmosphere already happened according to this particular record, but we still need to refine this and to check very carefully that we are using this position here and that this position of the microscopic ash deposit actually relates to the exact timing of the eruption and nothing else. And that's something that we need to work on. So this is where we're at in trying to compare and align these different records using our common tephra deposits. We can look at other examples. This one here, this particular tephra around 40,000 years ago, marks a very short-lived climate event in Greenland, but it'll be very interesting to see. At the moment, we can't see any evidence of this abrupt event affecting the ocean, which is quite interesting, but we need to increase the resolution of our climate proxy to see whether indeed there's any impact within the ocean. And so on, we can go back even to the last interglacial. Again, these are wiggles, different climate proxies, different climate records from different climate repositories. Again, it's the principle that I want to emphasize in how we are using the ash deposits that you can see, these lines that we're drawing, and then trying to align and compare these different records. So this is what I do, and this is where we're at with this particular question. So we're still working on why does climate change abruptly. Now, I'm nearly at the end, and I just want to share with you the results of some other exciting results. I've shown you results that I've been working on in the Atlantic region. I've mostly, for most of my research career to date, been working in the Atlantic region, North Atlantic, comparing the ice and comparing the marine cores. And as you remember, we've got this fantastic record of volcanic history. No tropical eruptions as yet found within the ice, but what we are finding, which is actually quite exciting, is that we're finding Pacific Arc tephras that originate from big volcanic eruptions that occurred within the Pacific Arc setting, from areas like Japan, from Kamchatka, Alaska, and also the Cascade. Now, there's been hints that we could find tephras from these sources, but our evidence in the ice demonstrates that big eruptions in the Pacific Arc actually repeatedly dispersed and deposited ash over Greenland during the last glacial period. And we've got 12 deposits during the last glacial period, ranging in age from 11,000 years ago to 80,000 years. So each red line here represents the different ash deposits. So our identity tag, we know they come from the Pacific Arc because the major elements that we show here, the different colours represent the different eruptions, and mostly, apart from these two, they sit outside the typical Icelandic envelope. And also then, if we delve into the trace and rare earth elements, the pattern that we see is very different from the grey pattern that we'd expect from Iceland. So we've got our fingerprint in this instance to trace it back to the Pacific Arc. So suddenly, rather than focusing on the Atlantic region, where Iceland has really been a major focus for me, I can actually now set my sights the other side of the globe and start thinking of the tephras that originate from the Pacific Arc. Because in Greenland, there's a potential for using the Pacific Arc tephras as a way to compare changes in the North Atlantic region with changes in the Pacific Ocean, merely by just using the tephras in the Greenland ice cores as a hinge point. So we've got tephras that have come all the way from Japan, almost 8,000 kilometres, being transported all the way to Greenland. Some of them are well known, Tawada, 16,000 years ago from Japan, and another one here from Mount St. Helens, 28,000 years ago. But more often than not, most of these we haven't been able to find a match. Now we know they come from an arc setting, and we know they come from the Pacific Arc, but more often than not, most of the others, we cannot actually find a distinct match. And just to show you this is don't worry about the detail, but this is just the list of the tephras we've found and the labels that have been given to them. If you look at the last two columns in this table, these are the possible volcanic sources that we have identified. Some of them are unknown, but we still think they come from the arc setting, but we haven't been able to find an exact source. But the potential tephra correlation, that is to specific eruptions, we have really struggled to find specific eruptions of the same age and same composition that match to our event. So from my perspective, these discoveries are really important for their use as correlation points, as type points, as our isochrons for looking at past climate changes. But I think their discovery also highlights that our volcanic history is very incomplete. So these were probably big eruptions that deposited ash over huge geographical areas, but there's very little evidence that we know of, at least, we've looked in the literature, there's very little evidence of their presence and preservation in areas very close to the volcanic centres. So although I'm really interested in reconstructing climate changes, I think their discovery and the discovery of the Pacific Arc also raises questions about ash clouds and aviation and the risks posed by some of these large ash clouds that we didn't know that occurred in the past. So there's also applications and significance in terms of looking at aviation risks here. And I'm quite excited by this shift from the North Atlantic region to the North Pacific. So very quickly then to sum up, we've gone on a bit of a journey in this particular lecture from the macro scale in Iceland, where we've got these beautifully preserved thick ash deposits, to the microscopic, where we are searching for needles in haystacks, and the application and step change in the application of this technique in the microscopic realm now means we can address some big scientific questions. And my big scientific question is to look at abrupt climate change. And from that, we've been looking at the ice sheet and linking the climate records preserved from the ice sheet with the climate records from the seabed. The geochemical fingerprint is crucial for that, and there are still some challenges that we need to overcome, but the geochemical fingerprint is particularly important. And although I've been working in the North Atlantic region for years now, my sights are set on the North Pacific and potentially using these ash clouds to really tie together a huge number of different climate archives throughout the Northern Hemisphere, not just the North Atlantic region. Just very quickly to finish, I would like to say a very big thank you to various group members that have been working on this particular issue and have made significant contributions to the work that I've presented to you today. There are PhD students, postdocs and technical staff that have made significant contributions. Without them, this work would not have been possible. Many of them have left Swansea now and have gone on to their next stage in their academic career. They are the next generation that I hope will take this technique forward, and I'm sure we'll see some exciting developments in the future. Thank you very much.
Wonderful. Thank you very much, Shuan. I always love in these lectures when we get a glimpse not just of the science that's been uncovered, but of what geoscientists actually do, and we get to hear and see what you get up to. I loved hearing about that. So we've got a little bit of time for some questions. There's a couple of microphones, so please wait for the microphone to come to you before asking your question. Who has a question? Oliver, let's go to this one first, and then...
Thank you for the really stimulating talk, and I'm really amazed at all the techniques. Are most of the particles, are they kind of like small spheres or little shards of glass, or what kind of shape are they?
I should have said that, but the image I showed you, they come in all sorts of shapes and sizes and all different colours depending on their composition. Some of the most beautifully preserved ones show they're almost butterfly shaped. That are Y-shaped because of the bubble junction as they've been erupted out of the volcano. So they, essentially think of them as fragmented glass particles with very sharp edges. Some are quite rounded, some are very sharp in terms of their morphology.
But they've got a large kind of surface to volume area.
Yes, to be transported that far. The basaltic ones that have a high iron composition tend to be quite blocky. The silicic ones tend to be a bit more delicate in their patterns, and we can see the beautiful bubble wall structures in some instances. Some contain air bubbles and vesicles. It just depends on the nature of their eruption.
Thanks.
There was another question to your left.
Thanks for your talk. Basically, has anybody tried tying this across to like biostrat or any other forms of stratigraphy, cyclostratigraphy?
Yes, so I've focused on the ice and the marine environment. We could also move into the terrestrial realm and to try and link to terrestrial records. There's all sorts of things, and I've just shown you how I'm applying it in terms of the abrupt climate change. Tephra Chronology can be used going back into deep time, looking at human evolution, human response, looking at glaciological change, all sorts of different areas that this technique can actually be applied. So there's the archaeological deposits as well.
And when you're associating it with certain volcanoes, are you doing that via the geochemical signature
Yes,
primarily?
yes. So we would compare our geochemical records with what's been published from proximal work near the volcanoes. So we know that they've come from, say, Katla or Grimsvötn. So we would always compare to a database.
And the final one is, are there any other global studies into this, using ice samples from elsewhere?
Global
Studies using ice samples from elsewhere or marine samples from, for example,
Yes.
Southeast Asia?
One of my postdocs
Yep.
that I showed, Peter Abbott, he's actually just he's moved to Switzerland just in the last few weeks, and he started a Marie Curie fellowship, and he is looking at applying similar techniques in the southern hemisphere. In terms of its global reach, the tephra is there are very few tephras that are global in extent. We'd like to find them. Toba was one, but the aerosols associated with volcanic eruption tend to be more global in their dispersal, but the aerosols that they leave in the geological record don't tell you which volcano it's erupted. So it's the tephra that actually allows you to pinpoint the exact source of the eruption. That's why it's so powerful.
Lovely. Cheers. Thank you.
Okay, thank you.
Okay, anyone else? There's a couple down towards the front, Sarah, thank you.
Thank you again for a fascinating talk. So you get your ice sample. How long does it take from extracting that from that wonderful ice store you showed us to having a complete analysis, or as complete as you tend to do? What's the time that it actually takes?
So for one sample, if you just had one sample, it would be quite quick, because all you want to do is to sample your side of your ice core, take the sample back to the laboratory, melt it, put it into a centrifuge tube, and that could probably be done within a week. Preparing your slide, microscopic analysis, that could be done in a week. What we then have to do is that we have our slide with our sample on it, and it's embedded in resin. Our ice core samples are embedded in resin. We've then got to painstakingly polish. If we find any ash particles, we've got to then painstakingly polish and grind away that resin to expose the particles so that we can actually zap it on the electron microprobe. That can take a little bit longer, but could be done within days. So one sample could probably be done from start to finish within a week, possibly 2 weeks. But if you imagine the number of the meters of ice that we've sampled, then it adds up, basically. But finding them, it isn't as hard as the marine environment. The marine environment involves a number of different steps, from sieving, density separation. There's also an acid step to remove all the calcareous material. So there are far more steps to move the host material and isolate the grains. The ice is quite quick. But to put a number on it is quite difficult. But I think it's the volume, the number of samples that we're looking at is what makes it a longer process as well.
Just in there, Sarah.
What was very revealing about your talk was that graph, which goes back 100,000 years and showed peaks and troughs going from cold to warm, which was, I think, 8 to 16, which is huge.
It is.
In terms of what we're worrying about today of 1 or 2 degrees. And the aspects of what's that new word, Anthropocene, which is, was revealing, atmospheric effect on climate change, oceanic effect, and you've been talking about geological effect, and then there's the human effect, isn't there? But those peaks and troughs, which were huge, going over a whole period, looks like there is no hope for not having continual earthly climate change, no matter what happens. But the main question I wanted, have you found a direct correlation between tephras, ash deposits, and spikes of those well, it'd be climate cooling, wouldn't it, for ash deposit?
We're looking at that at the moment and looking at the clustering of Icelandic eruptions in relation to the rapid climate transitions. We've sampled continuously between 25 and 45,000 years, specifically to do what you mentioned, to look at the clustering, to see whether any big climate jumps might actually result in waxing and waning of ice sheets that cover the volcanoes, which may actually trigger some of these volcanic eruptions. And that's something we're working on. We are not sure if there's a clear pattern as yet,
Right.
but we are looking at the clustering. If I go back to your first point, you're absolutely right in terms of the big temperature jumps. These are natural changes that occurred in the glacial period, so a very different climate regime to what we're looking at now. There is concern, of course, that, and trying to understand why they've happened, in order to try and understand why they've happened, is important to try and see whether they could happen in the future. But they happened during a very cold period, which is very different to today. And if you look at the IPCC, they are saying that these are unlikely to happen in the future, but there is suggestions that freshening of the North Atlantic could lead to a disruption of the oceanic circulation, which could then spiral into these abrupt climate changes. But
Generally, geology has quietened down, hasn't it, since the origins of time, and it'll go completely still at some point in the future.
Natural climate forcing is still occurring, as well as all these human-induced changes that we're seeing. So it's still ongoing, but the human-induced changes is what we are seeing. The warming is responsible for the warming we're seeing now.
Is there anyone else with a question apart from the gentleman who asked one before? If not, there's one more down here. Quick question, and then I'll come back to you, sir, at the end. Could you grab the microphone, sir, please? Could you just take the microphone?
Sorry.
You were saying that you couldn't identify the sources in some of these cases for these volcanoes. Is that because you were doing it by correlation with published data? Is it just the lack that there isn't sufficient published data out there, you think, on all these other events?
I think that's the case. It's that there's still a lot to be, a lot of work to be done in the proximal regions. A lot of the regions like Kamchatka is very remote. A lot of work has been published, but there's still a lot more that we need to look at. Possibly that some of the eruptions, the evidence may have been removed by glaciation, for example. The surprising one is that we're finding things possibly from Japan, and there's no evidence. Japan has a fantastic record of volcanic history, so you would have thought that what we find in Greenland we should be able to find in the proximal records, but as yet we're not. But I've been to a number of conferences where we've made a plea, if you've got anything that looks like these different eruptions, please come and talk to us, but we haven't been able to find a match to a number of those, to the majority of the Pacific Arc tephras.
Okay, and one final point here, Olivia. Thank you.
Would you expect the marine environment to warm up first, or the atmosphere to warm up first, and what would be the mechanism?
Nice simple question.
I think I'm not going to answer that, because that is something that we're trying to do and trying to use the ash deposits to look at them. I think they have to occur very close together. We can't really have we can't have a cold ocean and a warm atmosphere, for example, for a long time. But there potentially could be a lag. But that lag can't be very, very long. It can't be thousands of years. It has to be a few hundreds, or less, in terms of explaining that. But it's something that, watch this space, I'll say. Okay.
Thanks.
Good teaser for your next talk for us in a few years' time. Well, Paul Chouin has had to give this talk twice today, and I think it's been fantastic both times around, but we must let her and you come and have a drink with us now through in the lower library. But please join me again in thanking Chouin Davies.